Hello everyone, welcome back to LeetCode Daily. In this particular video, we are discussing LeetCode Daily Challenge, redundant connection. And in this problem, we have to given a tree is an undirected graph that is connected has a no cycles. And you have given a graph that started at a tree with n nodes and labeled with 1 to n with one additional edge we have to add, and added edge has no different vertices, and choose from 1 to n, and we have to uh, we have not an edge which is already exists, and the graph is represented as an array edges with the length n, and the range of this one is ai comma bi, and this edge between nodes from ai and bi in our graph, like there is some indices and all, and return an edge that can be removed so that the resulting graph is a tree of n nodes. If there is a multiple answer, we have to return the multiple answer, and so we have to find their last occur input we have to return. Like in this case, we have there 1, 2, and 3. This is the undirected graph, and let's suppose we have to go through 1 to 2, and 1 to 2, 1 to 3, and 1 to 3, and this 2 to 3, this 2 to 3, and we have to create a cyclic graph. We have to undirected cyclic graph, and now we have to return the last one, this last one 2 comma 3. So now let's look at their problem statement, then we have to discuss their example test cases so that you can understand how actually we have to iterate the values. And so here first we have to given in this problem we have to given a undirected graph with n nodes, and initially we have to forming a tree, and the tree is generally becoming tree is like first we have is connected, and is connected is basically there is a path between any two nodes, two path, and the second one is we have there has no cycle. And now however one additional edge is added to this tree and forming a graph with the exactly one cycle. So this statement we have to given here, like however one additional edge, let's suppose we have this type of here cycle, and then additional edge we have to put here. So here we have not create a cycle because one edge we have to add here, and you need to identify the edges that can be removed to make the graph as a tree again. Like here we have to form into a tree structure form, and 1 2 3 4 you can say, and this one is connected to 2 and 4, and this 2 is connected to 3, and this 4 is connected to their 3 you can say, and so you can 4 2 and here 3 and this one. Okay, and so we have to create a tree form so that you can identify easily, and if there are multiple edges that could be removed, so return the one that appears last in the input, and we have to return the last value which is the connected component, which we have to present on the problem. So now our goal is to identify, first we have to identify the edge in the graph that creates the cycle, and the second one we have written the edge. Okay, so now these are our given constraints, and now the constraint are we have to given the constraint are this is our n is equal to edges dot length, and so there is n edges we have to given, and this 3 less than is equal to n less than is equal to 1000, and the graph contains at least 3 nodes. These 3 nodes, at least 3 nodes, and each node we have 2 nodes of AI and BI, which is satisfy this condition of 1 less than is equal to AI less than BI less than is equal to edges dot length. And this basically we have to given like 1 less than is equal to AI and less than BI less than is equal to N, and so we have to given this one, and same thing for AI not is equal to B of I, and the edges cannot be connected with their nodes itself. So one given constraint for this one. And one thing is the edges are unique, and the unique edges we have, and the graph is initially connected, and so we have to given these types of constraints. So now let's look at their problem statement, and so that you sorry, example test cases, so that you can understand how actually we have to do such things, like we have to find their cycle and detect the cycle and find the connected components. And now first we have to given a 1 2 1 3 and 2 3, these are our edges. And first we have to take 1 comma 2, this edge, and this edge add an edge between 1 to 2, we have to connect with 1 to 2, and here is no cycle detected. And so now we have to add another edge for 1 2 3, and this 1 to 3 we have to add an edge between nodes 1 and 3. Okay, and 1 and 3 we have 1 edge 1 to 2 and 1 edge 1 to 3. And the same thing we have the last one, this 2 comma 3, and this 2 we have to add an edge between 2 to 3. Okay, the 2 to 3 we have their edge and this one. Okay, so now here we have to detect our cycle, because we have to move 1 to 2 and 2 to 3 and 3 to 1. This is our cycle, and you can again check with this one, 1 to 3 and 2 to 3 to 2 and 2 to 1. So this is undirected graph, and we have to move any of the direction. Okay, and now we have to detect our cycle, and the cycle detected of 2 comma 3, and this is our connected through our node 1 also. And now we have to answer the last one, which we have to get our cycle. Like here we have to got our cycle from 2 to 3, and so answer is edge 2 to 3 is our creates the cycle. Basically this one we have to create our cycle, we have to achieve our cycle. And now let's look at their example 2, so that you can understand actually work through two connected components, and how we create their um, edges between two nodes. And now we have first add edge of 1 comma 2, this 1 comma 2 we have to add an edge between 1 to 2, this 1 to 2. And now the second one we have to add an edge 2 to 3, this 2 to 3 here 2 to 3. And the second one this third one 3 to 4, we have to connect with 3 to 4. And one thing is, you have to take care, if there is an extra node we can discard it, because this is not create any cycle, or this is a not any connected component, this is not our connected component, this one. Okay, so you can discard it. And now 3 to 4 we have to connect, here is no cycle detected on at that point. So now we have to move further with 1 to 4, and this 1 to 4 we have to connect with 1 to 4, and now we have to detect our cycle, because we have to connect with 1 to 2, 2 to 3, 3 to 4 and 4 to 1. Okay, so now cycle detected from 1 to 4, and this 1 to 4, and this is our last edge, we have to connect with 1, again 1, and now we have to return 1 to 4, and this is our answer. this 1 to 4. So I hope you understand how actually we work and how we create their connected components, and like how their representation, like 1 to 2, 2 to 3, 3 to 4, and 4 to 1. And now the last edge is created our cycle, so that's why we have to return their value of edges, like which edge is create the cycle. So here 1 and 4. So now let's look at their problem coding implementation part. So here we have to use disjoint set union, so that we have to find their connected components and we have to detect their cycle. And now first we have their parent. This parent is actually work and to track their parent node from each node in the set, and this rank is track the rank of the set for balancing, like we have to check with their values with their edges. Okay, and now here we have to increase their size of 1 to n, and again we have to initialize node with 0, and this is our unset state. And then we have their for loop to iterate the parent and rank value, and this parent is actually each node is its own parent initially. Like first we have to start, let's suppose 1, so it is the parent of itself, and the rank all, here we have to all nodes have rank 0 initially, rank 0 initially. Okay, and now again we have their find function, and this find we have to find our values, and here we have if a node is its own parent, then we have to return root value. Okay, this root value, and then we have to check their path compression technique. Okay, path compression technique, and then we have to update the parent value, and then we have their union function, and the union function we have their first find the root parents, and the root parents of u comma v, and if the rank, yeah, here we have if the rank of if the rank of a is less than b, then we have to attach with a to b, and then same thing for here, if the rank of b is less than uh, a, and then we have to attach with b to a. And the same thing we have else condition, if the rank are equals, here equals, if the rank are equals, we have to attach a to b, and we have to increase b rank. Okay, so this is a simple union find function, and we have to use disjoint set. And now let's look at their main function, and this is our main function. We have to call their disjoint set, and the number of edges, since we have their edges here, and then disjoint set, and this disjoint set our initialize our structure, and then we have their for loop, and this for loop first we have to iterate all over the edges, all edges, and then we have to go with u and v, and the first we have to find the parent node of u and their parent node of v, and the same thing here. And now if else condition, we have to first, if u and v are different sets, this u and v are different sets, then we have to call, and we have to connect the components with disjoint set. Here we have to we have to union the sets of connected components. Okay, connected component, and now else we have to return the edges. Here we have to return the edges that creates the cycle. And now if there is no cycle found, we have to return the empty, like it shouldn't happen as per their constraint. So that's why we have to return empty array. And now the complexity analysis we have here. The complexity analysis. Okay, so first we have their time complexity. So the find and the union function, the find and union function is taking O of alpha n time, and where alpha n is the Ackermann function. So now we have to discuss their Ackermann function. So and the iterating through, we have to iterate through edges, these for loop, and now this taking O of n time. So now total time complexity of this code is O of n into alpha n, and this nearly of O of n solution. Okay, and now let's discuss this space complexity. The space complexity of this code is, we have their disjoint set data structure, we have to use O of n time, and the edge we have to store this taking O of n time, store edges, and now the total space complexity of this code is O of n time. And now I hope you understand how actually we have to work on this disjoint set union, and then we have to simply we have to track with values. Like this is the simple approach we have to follow here. And now let's look at their Ackermann function. And okay, the Ackermann function, we have to reverse inverse of which grows extremely slowly, and for all practical inputs. And like for example, you have to take n less than is equal to 10 to the power 9, and we have to nearly with our constraint. And now the actual value of alpha of n, the alpha of n is, let's suppose the n, here we have to create a table form. Okay, and this is our alpha of n, and this is, let's suppose here 10 to the power 3 and 10 to the power 6 and 10 to the power 18. Okay, and this 10 to the power 3 we have less than 4 value, and here less than 4 value, and there is less than 5 value. So here we have to calculate the alpha value with n value. We have to create a Ackermann function, and this simply we have to achieve their optimal solution, okay, by using union find. And so in real world application, the O of alpha of n is is efficiently treated as O of 1. This O of 1 is our constant time, and then this constant time becomes, because it is a not exceed, like not exceed any n time solution. So that's why we have to use this Ackermann function of alpha of n, because this is the constant time we have to getting here, like 10 to the power 18 is less than 5 time, less than is equal to 5 times. So that's why we have to use a union find here. And now I hope you understand how actually we have to work with their edges, and we have to detect their cycles. And now thank you everyone, thank you so much.